Equivalence, and the sign of the equal is like equal, and equivalence in the integers is basically if I say 1 by 3 and that is equal to 3 by 9, so both are equal, we know that, but in the integers we say this is equivalence relationship. For the given set of the triangle, this relationship is similar as with this symbol. With this symbol you can say that the equivalence, the relation, and it is the congruent to this. So equivalence for the given set of the integer, the relation is congruence and modulo. So like this is the sign is for the specific modulo, and they show equivalence. If you see somewhere like this symbol, you understand that there is a congruence relation between the integers, and this is the basic symbol of the uh, equivalence relation. Okay, so understand the basic. Okay, let's do it, and I understand equivalence relation definition. So a relation R is a set of the A is said to be equivalence relation if and only if the relation is a reflexive, symmetric, and the transversive. So if the relation is a the relative, reflexive, symmetric, and transitive, the equivalence relationship on the set, which is generally represented by this symbol. If you see somewhere like this symbol, it's meaning that equivalence relation, and it's like reflexive and symmetric, transitive. A relation is said to be reflexive if a comma in this symbol with r is equal to be this symbol. This is the meaning of the belonging symbol. So this is symbol, so this belong to this one, I mean a small a belong to capital A. And the symmetric is the relation is said to be symmetric if the a comma b and this symbol is belonging to R, then B comma A is belonging to capital R. Then talking about the transitive, a relation is said to be transitive if A comma B is belonging to capital R and B comma C belonging to capital R, then A comma C belong to capital R. In this term of the equivalence relation notation, it's define the follow the binary relation on the set of this set to be equivalence relation if one only if the reflexive, symmetric, and transitive for the all x, y, z, and set A for the x, and this belong to reflexivity and x equivalence to the y, and if only y equivalence to x, this is symmetry, and x equivalence to y, the y equivalent to z, then x equivalent z is transitivity. This equivalence relation can be explained in the term of the following example. The sign of the equal is like this is the sign of the equal on the set of the numbers. For example, 1 divided by 3 equal to 3 divided by 9. And for the given set of the triangle, relation is similar for the equivalence, and this is the symbol for the equivalence relation, and this is symbol for the congruence relation on the set to show the equivalence. For the given set of the integers, the relation of the congruence modulo. So this is the equivalence class partition. So the equivalence, this image and domains are the same under the function, which show the relation of the equivalence for a set of the all images has to same cosine for the set of the all real number has the same absolute value. Equivalence relationship proof. Here are the equivalence relationship example to prove that property. Let us assume that the capital R and let us assume that the capital R be the relation on this set of the ordered pair in the positive integer such that A comma B, C comma D belong to capital R if and only if AD equal to BC is like a capital R equivalence relation. In order to prove that R is equivalence to the relation, we must show that capital R is reflexive, symmetric, and transitive. This proof is given condition like with the reflexive property. So according to the reflexive property, if A comma A belong to capital R, A comma A belong to capital R, for the every A belong to capital A, for all pairs of the positive integers A comma B and A comma B belong to capital R, clearly we can say that AB equal to AB for all the positive integers. So it's a meaning this is the reflexive property. Hence the reflexive property is proved. Symmetric property, for the symmetric property if A comma B and belong to capital R, then we can say B comma A belong to capital R for the given condition. A comma B, C comma D and belong to capital R, then C comma D and A comma B belong to capital R. If A comma B and C comma D belong to capital R, then AD equal to BC and CD equal to DA. Since the multiplication is commutative means like we have to add the product, and therefore C comma D and A comma B belong to capital R. Hence symmetry property is proved. Now talk about the transitive properties. So if A comma B belong to capital R and B comma C belong to capital R, then A comma C also belong to capital R. So for the given ordered pair of the positive integers, we have to A comma B, then comma, then C comma D belong to capital R and C comma D. E comma F belong to capital R, then A comma B and E comma F belong to capital R. Now assume that A comma B and C comma D belong to capital R and C comma D and E comma F belong to capital R. Then we get the D comma B equal to CB and the CF equal to DE. So the above relation implies the A divided by B and the equal to C divided D, and that's C divided D equal to E divided F. That therefore the A comma B and E comma F is going to belong to R. Hence this transitive property is proved. Okay, so let's see equivalence relation examples and go through the equivalence relation example solution provided here. So let us assume that F is a relation on this set R. You have some real numbers defined on the yx fy. If and only if x comma y, x and y is integers, prove that F is a equivalence relation on R. Solution is like a reflexive. Consider x belong to R and then x the minus x equal to 0 and which is an integer. So therefore x fx symmetry is like consider x and y belong to capital R and the x fy, then x minus y is an integer, thus y x minus x equal to minus x comma minus y minus x. Yeah, otherwise you can say y x. It is also integer, therefore y fx. Transitive, considered x and y belong to capital R, which is be reflexive, we can say x fy and y of z. Therefore x, y and y z are the integers. According to the transitive property, x minus y plus y minus z equal to x minus z it is also a type of the integers. So that x fx, thus capital R, which is become known as a reflexive, is an equivalence relation on the R, showing that the relation R is an equivalence relation in the set of the capital A equal to 1 comma 2 comma 3 comma 4 comma 5, given by the relationship R equal to A comma B, where the solution is, you can say, capital R equal to A comma B and the sample of the division A minus B is given, where A comma and B belong to capital A. This is the reflexive property from the given relation. You see A minus A is going to be equal to 0 and 0 is always even, not odd. So thus A minus A is even, therefore A comma A belong to capital R. Here R is a reflexive symmetric property from the given relation. A minus B is equal to B minus A. We know that A minus B is equal to minus B minus A, and the B minus A is even, so that B minus A is also even. Therefore if A comma B is belonging to R, then B comma A belong to capital R. Hence capital R is a symmetric. Transitive property is A minus B is even, then A minus B is even. Similarly, if B comma C is even, then B comma C is also even. So if the even number is also even, so we can write it A plus minus B and plus B minus C is even. Equivalence relationship practice questions. For understanding what is the even and odd number, you can see here, odd numbers are those numbers which can be divided into two equal parts, whereas even numbers are those that cannot be divided into two equal parts. Example of the odd number is 3, and odd number, those numbers that cannot divided by the two equal parts. So 3 cannot divide by the two equal parts. 5, 7, 9, they are the odd number. Even numbers are the 2, 4, 6, 8, 12, 14. So they can be divided into the two equal parts. So it's an even number, and which cannot be divided into two parts, called as a odd number.